Thank you very much. So good afternoon. As Annika was saying, I have on the screen some visualization of some of our GCM simulations. In this case, at 5 kilometers, this is sort of a next generation HighResMIP, or sort of a legacy of Primavera. This was part of a diamond experiment that Bjorn Stevens initiated and we took part in. And this is just to give you an idea that we can use nowadays a full-fledged climate model, exactly as we used in CMIP 6, and particularly for HighResMIP, which I'll talk about today, and put it through very crude initialization without data simulation, sort of emulating a weather prediction, and test and assess a climate model as we would a weather forecast. And in this case, we just slightly altered the initial conditions. And if you follow the flow, if you look at the easterly waves, which are traveling from Africa to the north of South America, you will see in the path some hurricanes developing, which is one of the prominent phenomena that develop at high resolution in these weather and climate models. And as the evolution of the simulation takes these three ensemble members away from each other in the weather and or sort of seasonal trajectory, you will see hurricanes developing, and while at the very start the hurricanes are exactly at the same position because of chaos, because of uncertainty in initial conditions, these hurricanes end up developing in very different regions already in the short time span of one of these diamond simulations. So this is telling you there is a hurricane right now in ensemble member 2, bang in the middle of the Atlantic, going up to mid-latitudes, which is also a topic I will try and cover today. Right, let me stop this and switch to the proper presentation. See if my PowerPoint will collaborate. Here we are. I hope you can all see now my slides. And I have the same animation, but I'll skip. So I'll talk a little bit about modeling and predicting changes in climate and hazardous weather, with this notion that weather is basically the building block of climate. And we do expect incredible climate simulations to have these weather elements and to be able to trace them and understand them and see how these weather elements form the climate. So I'll start from end user needs and then go to climate science. This is an example of natural catastrophe. So the insurance and reinsurance industries put out these catalogs once a year where they detail what has happened in the course of a whole year, and they classify events as hydrometeorological, so it's blue and green, what they call hydromet, and then geophysical, like earthquakes, and then things like wildfires. And they attribute losses to these events. And here at the bottom, we have the sort of recent benchmark here, 2011. These are natural catastrophes for the whole year, a loss of 380 US billion worldwide. 2017 was well, I haven't looked at 2020 yet, but 2017 was the second largest loss, 300 US billion. And there is a very strong question from industry about whether or not the number of events, there is a time series here going from 1980 to more recent times. There's a question as to whether or not these events are increasing in time, so these loss events that they call. And you can see also the hydromet, so the green and blue are the majority of these events. If you look at the actual monetary loss, this fluctuates quite a bit, but they do believe that maybe there's a rapid increase. But you can see that the years of maximum number do not correspond with the years of maximum loss, and a lot of this has to do with exposure. So you can have a lot of natural catastrophes, but if they don't hit any assets, there is no loss. Of course, there's very likely going to be loss of life, but this is not what insurance care about. They care about their revenues. The point is to understand the connection between the hazard and the losses, we do need models that are able to connect the different phenomena worldwide and are able to credibly represent the distribution of these phenomena worldwide. And the motivation is not just insurance, because, as I said, we're talking about hundreds of billions of dollars each year, but 2/3 of that are uninsured. It means people in the poorer regions of the world, and you can see, for instance, in Africa, only 1% of the assets are insured. they are exposed. They lose their homes, they lose their business, and nobody's going to rebuild for them. So there is a need to do this globally, and there is a need to do this at higher resolution to credibly estimate the risks. And another aspect of this is that governments and businesses are unable to plan what society should do because there is no reliable information. And sometimes GCMs, especially high resolution GCMs, can help us complement the observations where the observations are either incomplete or unreliable. Well, I will talk a bit about hurricanes, and I just want to use hurricanes as an example of things that in Europe we are currently not exposed to, but we might be. And anyway, so I'm talking about direct exposure. So hurricanes do not usually come all the way out to our shores, although we had a close call with Ophelia quite recently. And we do have a phenomenon called medicanes, which are very small but very intense cyclones that do bear some of the characteristics of hurricanes. We had one just in this past year. But we do have indirect exposure because of our financial exposure, because the global marketplace is interconnected. And also we have exposure because many of these storms actually undergo extratropical transition and end up reaching our shores in a different form, and I'll show you how later on. So no matter how we look at this, there is some form of exposure to things that are extreme, things that are normally seen as tropical. And even the US military are thinking a lot about this because each one of these storms has a very severe impact. And so they're also thinking globally. So anyway, just remember this notion of global, interconnected, teleconnections in the physical space, teleconnections in the financial or societal space, and high resolution. So, well, we've been building models for a very long time. The set of equations is complex. The set of equations is spanning, in terms of the phenomena, a very wide range of spatial and temporal scales. We often have to filter these equations. We have to simplify in order to be able to solve on a three-dimensional grid. And basically, every time we discretize and we form either finer spatial resolution or a more accurate type of prediction, we incur costs in terms of the number of points we're computing, but also the time step has to become shorter accordingly, and the integration becomes more and more expensive. So unfortunately, we've been trying to assess risks and project future risks, trying to simulate the impact of these forces on the wind and on temperature and precipitation and all that with very coarse models and often inadequate models that do not contain the phenomena. So global models, well, of course, and this is this typical CMIP exercise, they offer global coverage, they offer us many types of scenarios and offer us the ability to do some form of attribution, and they enable us to make predictions and ensemble predictions, heterogeneous ensemble predictions, but they're mostly designed with the idea that what happens at the large scale will cascade down to the local scale. So these local phenomena can be studied and seen in terms of their impacts just regionally without looking at these global interconnections, these teleconnections in physical or sociological space. The models as they are in the IPCC traditionally are coarse, and the information is not suitable for regional, and the traditional way to do this is to use regional models like we do with Cordex. But we do know that there are missing processes, and if these missing processes should have an impact on the large scale circulation, this would invalidate the use of global models and the cascade to regional models. So that's an open question. So thinking about these ideas, we decided to embark on an experiment in which we would use multiple models at low and high resolution. And this was behind the design of this new protocol called HighResMIP. And the idea is to resolve globally the boundary conditions and the actual atmospheric flow and see what this will do to things, for instance, like extreme precipitation across the Gulf Stream region and downstream, what this extreme precipitation will look like in Europe. And you can already see some hints of precipitation interacting with orography around the Alps, around the Scandinavian Alps, around the little bit of orography we have in the UK. But potentially also there is something that could be different in places where you have boundary currents or where you have important conversion zones, and the precipitation field could be quite different, and other atmospheric fields could be quite different around those regions of strong convergence or strong air, sea, or land atmosphere interactions. So that was a bit the idea of setting up Primavera. We set up the project to coordinate a number of European GCMs, and 6 participated, and to form a consortium to run quite a long protocol at very high resolution and to submit the results to the CIMIP6 exercise, and to be able to also assess the models at the process level and see whether they would be better able to simulate societally important processes, both in terms of their impacts and in terms of their interactions, and whether the climate trajectory would be at all different because of these processes. And so would this give us an idea of risk for Europe that is different from the traditional view of risk? And I'll show some examples of this. Just to say that much of this revolves around resolution, and well, we know from NWP that in the 40-year progression of the improvement in forecast skill and also the homogenization of the skill between the 2 hemispheres, many elements have contributed. One of them is data assimilation, the other one is model formulation, so the quality of the parameterizations, the inclusion of processes, for instance, nowadays the coupling to the ocean, even in the NWP world. But some of the progress at the different times has been due to resolution, which has also improved dramatically. And nowadays we do weather forecasting at around 10-kilometer resolution globally. The climate models have not progressed so quickly. So it was sort of, for us, time to say, okay, what if we were to do climate modeling with the same spirit that has inspired the NWP people? And some of the frustration has been that when we look at the projections of climate change, for instance, this is a projection of precipitation change. There are many areas of the world that with the traditional approach of coarse CIMIP models cannot even agree on the sign, and there are very few places where the projections, even in terms of sign and magnitude, are robust, particularly so for summer. So the idea was to try and move away a little bit from this and see whether we could do any better with higher resolution models. Just to say what it is that we mean by high resolution. So this is an example of what the Alps look like in a typical IPCC model. So about in the range of 100 to 200 kilometer resolution. This is what the Alps look like in a weather GCM of a few years ago, or in HighResMIP, what we were trying to do in Primavera. So the idea was to run climate at this resolution, and then to run climate at this resolution, and then also as a projection to the next CIMIP to develop models in this space, sub 10 kilometers. But this was the core of HighResMIP, to run experiments at these 2 resolutions and compare and understand what the role of resolution is. So this is an example from the current CIMIP archive of what the resolution space is. So many models are still running 1 degree ocean models. For this is the deck experiments. And a few are running at half, or maybe a handful are running at 1/4 degree, but still the atmospheric resolution is rather poor. In Primavera, we have a much, so this is the HighResMIP, and it's Primavera plus a number of other groups worldwide. We have quite a continuum of resolutions down to even 1/12 of a degree for a select few models, and many of them running at, as I said, 20-25 kilometer atmospheric resolution. So this is really quite a change compared to the standard deck experiments. The protocol required that people run AMIP simulations for 100 years, starting in 1950. So a hindcast, quite a long hindcast, and a short prediction period up to 2050. And then in coupled mode, a control experiment with constant 1950s forcing, and then a coupled historic experiment that mimics what we did with the AMIP. And as I said, 6 European GCMs participated, and coupled the system usually at low and high, and a few of us tried also the mix of high-low and low-high between, so the cross resolution between ocean and atmosphere. Overall, we've used about 503 million core hours, which is 10% of the total European CIMIP effort, and wrote about 10 petabytes to disk. Actually, it was more. This is the usable bit that we wrote to disk. And we delivered about 2 petabytes, which is rather comparable to the entire previous CIMIP exercise. So it was a rather large effort, but it was manageable. We could do it. So just to just take a brief look at some of the outcomes. This is a plot that came out of ESMVal tool. Since all the data are now on the portal, it's possible to invoke the ESMVal tool and to look at errors, for instance, in the simulation of surface temperature. And this is an example of the bias in SIMI5 models, SIMI3 models. This is the current set. And this down here is the bias in the high resolution part of HighResMIP and the low resolution part of HighResMIP. So in a sense, this is a select group of these. So these models also did the DEX, but here they follow the HighResMIP protocol and here they don't. And you can see there are some notable errors that have been around for the last 20 years, particularly in the star cumulus regions, but also there are some strong biases over some of the continents. And one of the first things that you can notice here is how these errors have improved. 1, 2, 3 have improved, and also over some of the continents, some of the errors have improved. On the other hand, you can see that comparing the low resolution and the high resolution, because this is quarter-degree oceans, we now have a Southern Ocean bias, which actually, if you go to the next generation, the one that was not submitted to CIMIP6, at 1/12 degree, this error also disappears. And we have a number of metrics, and overall, I would say for global climate, if you take global figures, things are not terribly impressive. It's where we go down to regional estimates of things that things look a little bit more interesting. As I said, process approach. So people have been looking at a number of things. This is an example of looking at the trimodal distribution of the jet in our part of the world, and whether or not these high resolution models can better reproduce that, and they do. And then looking at the importance of resolution for blocking. So this is Randa Sheeman looking at atmospheric GCMs and AO GCMs and looking at whether or not the frequency of blocking events and the spatial correlations, so looking at 2D maps of where the blocking is, and also looking at the RMS, whether or not resolution that has an impact. And in this case, I would say that the outcome is not terribly impressive. There are some improvements regionally for winter, and definitely it is not terribly impressive over summer. But this was a very important, it's important to look at things and not be prejudiced and wanting to see positive results. What is definitely true is that the CIMIP6 models are way better than CIMIP5 models in terms of blocking, but we're still rather far away from observations. The connection between the eddy-driven jet and blocking is, however, quite well represented. This metric that is also available through ESMVal tool shows where the obs should be, and many of the models, as they go from low resolution to high resolution, a much better connection between the jet and the blocking frequency. So that, in terms of processes being connected to each other, is an important progress. Now, I showed you before a map of the projections of precipitation by CIMIP models in the last at least 2 rounds, and the frustration that we've been experiencing because they cannot agree on the sign and the location of these changes. This is a paper by Benoit Vanier that was published a while ago, showing what happens as we increase the resolution in AMIP mode and CIMIP, so coupled mode, and on the right-hand side. The colors here show in these long hindcasts that we did, it shows the change of precipitation with resolution now, not with climate change. So where it's blue, we have more precipitation. And if you look very carefully, you will see that it happens over regions of high mountains, but also over places like the boundary currents, both here and here. And also you can see that in major convergence regions, we have now a concentration of the increasing precipitation, and potentially we also see a narrowing of the ITCZ and also signals around the maritime continent that we've seen before. What is really important about this plot is that the stippling indicates that the models agree. So the protocol being very strict and the dynamics being much better defined gives us a larger level of agreement between the individual models in PRIMAVERA-HighResMIP. And when we compare this to observations, so these are 2 observational products for precipitation, and we see whether or not increasing the resolution makes the bias worse or decreases the bias. So whatever the colors are brown, it means the error is reduced. And again, if you follow it carefully, you can see that there are places around the ITCZ or around orography or around the maritime continent where the errors are reduced indeed. There is a very notable error here in couple mode, has been around for a very, very long time. This is an enormous error and has plagued CMIP models forever, and now is severely improved. There are places, for instance, down here in the South Pacific, where perhaps the models are now exaggerating the precipitation field, but perhaps also we need to question how much we know about precipitation in such regions, and I'll come back to this in a different context. But what I want to say is one of the most important things is that there is a very large degree of agreement between the GCMs that participated, both because of how strict the protocol is and because of the impact of dynamics now, very well resolved dynamics. Somebody ran an intercomparison between the previous approach, which is to take coarse global models and then to downscale them, and compared this to Primavera models. And this is an example of looking at the distribution of precipitation rates and how much each one of those bins contributes to daily precipitation in various European regions. And the conclusion of the paper is a very long, very detailed paper. I invite you to read it if you're interested in this, is that actually for winter in many of these regions, the Primavera GCMs provide more valuable information about the precipitation distribution, so this frequency intensity distribution, than the downscaling method does. So that's interesting. That was not actually what we intended to do. This was not one of our objectives. We didn't want to compete with the regional models, but it gives us a benchmark for not just the spatial distribution, but also the distribution in time of the precipitation field, despite being still very far away from the regime of resolution where we would reproduce the high intensity convective events. Going back to the Primavera models, we looked at whether the precipitation response was the same everywhere or was mostly orographic. So we used a technique to separate orographic precipitation from anything else. And as we go from coarse to quite high resolution, we can see that definitely the orographic precipitation increases. So this amount of land precipitation that is due to the interaction with the orography is certainly emerging in these Primavera models, while the resolution dependence for non-orographic precipitation is rather flat. So this is where it mostly happens. And we use then techniques to exploit the global river network to look at whether or not the fact that now we rain over mountain ranges and we don't rain, for instance, to the lee of mountains or in places where the orography is not so prominent is a good thing. And if we compare globally over various catchments, we looked at hundreds of rivers throughout the whole integration period, we can easily say that compared to what was observed in the river discharge, the high resolution simulations, particularly where the orography is very prominent, definitely give us a much better estimate of river discharge than the coarse resolution simulations. And this was something that we already knew from regional modeling. It's been done in many parts of the world, but we can now do it with a global model. And the advantage of doing that is that for a very long time, we've known that, so there was a paper by Marie-Estelle Damory about 10 years ago, and this was repeated by Benoit Vanier more recently with his new data. We know that as we increase the resolution, the hydrological cycle that we simulate is more vigorous. We rain less over the ocean, we transport more to the land, we rain more over the land, and then we think that there is more return to the oceans. But until now, we didn't really know what this number was. And by integrating all the rivers simulated by all the Primavera GCMs with the same river discharge model, we were able to come up with an estimate of this return of the hydrological cycle to the ocean, which is this number, 50. These are very funny units. It's cubic kilometers, I think, per year. I forget now what the unit is. But this is what the observations that we've derived tell us. When we drive the models with actual observed fields, we get this number. And if we were to use the low resolution GCMs to estimate this return to the ocean, we would severely underestimate this number. These are other estimates from other studies that tell us that very likely what is derived from newer observations and observations that integrate remote sensing and all that comes very close to our estimate and definitely comes very close to what the higher resolution models do. So it's not just that we can resolve the precipitation in the two domains, and we can very carefully compute the moisture conversions over the continent, so we can close this bit. But when you go and try to close this bit, we also end up with a very consistent picture of water being returned to the oceans at high resolution. And this also implies that actually, over many parts of the world, especially at high elevation, where the observations are difficult or inconsistent or missing, it rains more than many of the data sets that go behind these studies, particularly the old ones, imply. So things that have come out in the last 5 years, for instance, by Graham Stevens, implying that it rains much more over the continents than we think it does, also at high latitudes, are very likely the correct estimate. And our study supports that. Yeah, I'll skip because I've already said it. Another aspect, so I'll dwell for a few minutes on this, and then I'll show you the ocean correspondent bit. For many years, people have talked about land-atmosphere coupling. That is the regions where the state of the land surface, so for instance, the Bowen ratio, very much determines what happens at that location. And this, for instance, can be seen as how much evaporation goes in the atmosphere and how much of the precipitation that falls locally is due to that local evaporation. And indices have been created to say what are the hotspots. In red here are the hotspots of land atmosphere coming throughout spring, summer, autumn, and winter for the Northern Hemisphere. And we decided that we would look at whether or not increasing the resolution changes this coupling. And you can see in these two colors, there are regions where in red we have a positive change, and regions in blue where we have a negative change. And one of the examples is Australia. But in many parts of the world, we actually see a meridional shift, which is rather interesting. And we focus down on the region of the Sahel because it's very important for agriculture and the sustainability of agricultural practice, but also it's very important for the moist flow that ends up in easterly waves, causing growth of organized systems and potentially can seed hurricanes. And what we see in this region, this is what happens. We see a reduction of the coupling strength to the south and an increase of the coupling strength to the north. These are very big regions, and these are very big numbers. This is the ensemble agreement in Primavera models. All the Primavera models give us this signal. This is summer for atmosphere only, and this is summer for coupled. And then we have again the autumn atmosphere only and the autumn coupled. And we went through and looked at all the components, so evaporation, precipitation, and we looked at the vorticity field, we looked at many things. And what we discovered is what happens here is that the vorticity field is organized quite differently in the domain because of the mountains that are in this part of the domain. And the way the precipitation is formed, the way the moisture converges into the box and the way the precipitation is formed causes this strong increase in coupling between evaporation and precipitation in this region and a loss of coupling to the south. And this is really important because it means that we make the precipitation region both narrower and also shifted to the north. And this is actually very, very important for deciding how we run regional models and how we should draw conclusions about particularly water resources for agriculture in this region. We really must think very carefully of which models we select out of the whole of the CIMI6 archive to drive regional models. So anyway, this has been published very recently in Journal of Climate. I switch now to the ocean, and I show you some examples of the impact of going from 1 degree ocean models to 1/4 degree all the way to eddy rich models at 1/12 degree. As I showed you before, already this has an impact on the temperature near the surface of the ocean. So there are places where the temperatures increase and there are places where the temperatures decrease. And if you look at this in terms of bias, there are places where this means that we are reducing biases, but also at a 1/4 degree, there are places, as I said before, where the bias is worsened. And we need to go to the next resolution, 1/12 degree, to improve this. But already these errors in the North Atlantic and basically throughout the North Atlantic basin are important errors that have been reduced by using 1/4 degree models. And Malcolm has a paper and also Jackson et al. Have a paper in which they show that the models are able to resolve a stronger overturning circulation. And also, if you apply these models to climate change, the change in the overturning circulation very much depends on having this strong circulation. And Malcolm has looked at whether or not the AMOC and the North Atlantic heat transport are better resolved as we go, are better simulated as we increase the resolution. So these are observations, and these are different models at these resolutions. And as you go through to a quarter degree, we have improved agreement. I would say it is a slight improvement. I wouldn't say it's so dramatic. But as we go then to a 112 degree model, and there are only two in Primavera, we have a very, very strong agreement with the observations. I think this is major progress for ocean modeling. And Alessio Bellucci et al. Have also looked at air-sea interactions. And basically, they're looking at different regimes, and they're showing what happens also with these lead lag correlations between the SST tendencies and the sorry sorry. We have some covariance patterns that develop over the oceans in low resolution and high resolution. As we compare these two observations, these patterns are much more. These are the observations here. These patterns, both 1 month before and 1 month after, much more realistic compared to the observations in the eddy permitting models. There is a paper now talking about the consequences of resolving the ocean more credibly, and where the 15-degree isotherm is, the in black is the observations, and many of the traditional CIMIP models have this error here, and then downstream become way too zonal and have quite an error in the position of that isoline, while the higher resolution models, even driven with a mid-resolution atmosphere, are able to capture this. And there is a paper by Moreno Chamorro et al. That shows that actually, if we then do climate change and we look at precipitation over Europe, particularly extreme precipitation, running with a configuration that gives us this response to the air-sea interactions in this region, gives us both an extreme of precipitation in this region, but also over Europe. So if you are looking at projections of extreme precipitation for Europe from the classic SIM6 models, from UKCP, and even from the HighResMIP models that use still an eddy permitting but not eddy resolving models, we get a reasonable increase in precipitation. But if we go for this type of model, we end up with some very strong surprises, something very, very alarming in terms of the precipitation, extreme precipitation change for Europe. So very strong downstream events by simulating something that is happening just in this region and the interactions of the atmosphere with the ocean in this region. Sorry, let me drink a little bit of water. So I started this with an animation in which I was looking at hurricanes. Hurricanes are a very fascinating phenomenon, but also we think they are very important in the climate system. We've been looking at the role of high resolution for hurricanes for a very long time. And in one of the studies we had about 5 years ago, an intercomparison of GCMs between Europe, US, and Japan showed us that as we go from about 100 kilometers to 20 kilometers, we definitely increase the number of hurricanes we simulate each year to between 80 and 100, which very much agrees with the observations. This is our model here as we go through sort of low to medium to high resolution. This is CAM, and there are other examples of models that are run a different resolution and give us a higher number of hurricanes. This is important to us, not just because of what I said before, because we are financially exposed, but because projections, this is an example from Ryan Harsma, who was one of the people who designed HighResMIP, showing that in the future with Easy Earth model, many more storms of tropical origin will impact Europe, and they will actually bring much precipitation and wind, extremes of precipitation and wind to our shores, something that doesn't happen currently, but is projected to happen in the future. So we need to know whether or not any of the models are good, and one way to know is to exploit variability. So this is an example of observed variability in the North Atlantic. There was a maximum in 2005, a very, very powerful season. We just had another maximum this year, 2020, with so many hurricanes we ran out of names. And as we look at the product of these GCMs, they not only produce more hurricanes, but they're better and better able to resolve the interannual variability and the skill at resolving interannual variability. So this is a low resolution model and this is a high resolution model. They have all of them, and I'll point you to the right papers to look at the summary for Primavera. They all managed to reproduce these extreme years. So that is reassuring in terms of at least understanding the variability aspect and possibly the changes in variability of hurricanes for the future. In terms of the means, this is what the tropical cyclone storm tracks look like. So this is the number of storms that go through a particular grid box in a given month or year. So this is what observations tell us currently. This is the places where the hurricanes live and die. So the Atlantic, East Pacific, West Pacific, and the Indian Ocean, and the Southwest Pacific. This is what, this is also extracted from a reanalysis here. This is what an ensemble of models at low resolution does, and you will see mostly that the Atlantic is missing. Many of them are unable to reproduce Atlantic hurricanes. And as we increase the resolution, we have a far better representation, particularly for models like the French model, and I would even say our own model, the HadGem3. The Atlantic storm track is much better resolved. And you can see that over the West Pacific also we have quite an increase, and potentially over the East Pacific and maybe over the Southwest Pacific, we're now maybe exaggerating, but we had a paper analyzing reanalysis and what the reanalysis tell us, and maybe suggesting that the models are now producing storms in places where nobody's looking. So that's again alerting us to the future. In terms of structures and the abundance of the low categories, so the very weak categories at low resolution, so these are the different Primavera models. These are the very weak categories all the way to category 5, the most severe hurricanes. So at low resolution, we have a huge number of extremely weak and undefined storms. As we increase the resolution, we produce far less of those, and we start to produce something that is starting to resemble, at least from the point of view of pressure, start to resemble the structure and the number of storms in the upper categories. I still think that categories 4 and 5 are severely underestimated, but we're starting to have a few, particularly in the French model, we start to have a few of these very intense ones. We're starting to come close to what is needed for this problem. The other aspect of Primavera, because we ran the experiments for a very long period of time, there is, in some basins like the Atlantic, there is very strong decadal variability. So we've gone through a minimum between the 60s and the 90s, and then we are now experiencing a maximum. And when we run the models in freestyle without forcing, we just look at natural variability. As we increase the resolution to about 20 kilometers, we are able to reproduce this decadal variability, and even able, so these are the individual years, these are smoothed versions of that line. We are able to reproduce years that look even more extreme than 2005, which was the, this one, which was the previous maximum. And potentially this now is starting to look very much like 2020. And this was done with a model that doesn't even have anthropogenic climate forcing in it. But the notion of variability is very important. In terms of the projection of the mean change of hurricanes with climate change, we had in the past some experiments, and we showed that there is a very strong poleward migration in the Pacific. So these are 3 different resolutions, and potentially a reduction in Atlantic hurricanes, or even an equatorward. Some of the observations are telling us that we expect an equatorward migration in this basin. I would say this one is the bit that agrees with at least a bit of observation we have now. This is what the change in hurricanes looks like between the end of the Primavera integration, so up to 2050, minus the current period, at low resolution and high resolution. And you can see that actually the models reproduce some of this Central Pacific and maybe Western Pacific reduction, but they're not, I don't see any evidence here of the models reproducing this increase or this poleward migration. And definitely they also do something rather odd in that some of them produce an increase in the Atlantic. However, this is with rather weak forcing. So if we were to use, and I'll show you in a few minutes, another projection which with a much stronger forcing that belongs more to the end of the century, which is what this was, perhaps then we will start to see this other part of the projection. Another interesting example is looking at these storms that make landfall in North America, like Sandy did in 2012, producing $70 billion damage, and storms that make landfall in Europe. We've gone through the various reanalyses that we have, and we looked at how many, and it's a handful per year, but they are happening, impact these two regions, and also what their nature is. And it is true that in both cases, even just looking at the reanalyses, a number of them are able to come to these very high latitudes, still as warm cores, so still as proper hurricanes, although most of them undergo extratropical transition and end up looking like the normal mid-latitude storm. And this is important because, in fact, in terms of wind speed and also in terms of precipitation, which I don't show here, the nature as they strike our shores is rather different. And also how they evolve after they make landfall is rather different. So it's the type of threat, the type of impact they cause is rather different. So being able to trace them and to understand what they are and to project what will happen in the future based on these individual storms is very important to properly look at risk. I'll say a few things about physical parameterizations, but I can see that I'm nearly the end. Maybe I should actually skip this. Just to say that Primavera was not just about resolution, it was also about developing a particular aerosol scheme that very much simplified aerosols, and here I show the arrows, and I would say it doesn't look much different from other SIMIP6 models, despite being a simplified treatment of aerosols. The radiative errors very much reflect the temperature errors, and in general, we can say these models at high resolution have improved, particularly in the stratocumulus regions. I'll skip the land surface here and the sea ice. There was a lot of work in ocean mixing, and it's definitely true that the new ocean mixing schemes have very much improved the simulation of part of what we've seen in terms of North Atlantic, and even in parts of the Southern Ocean at the surface. However, the different mixing schemes that were producing Primavera produced a very different internal ocean configuration. And perhaps this tells us that the protocol was not long enough for these new schemes to be really tested in anger and at the proper resolution. So maybe this was a bit of a shortcoming of Primavera from that point of view. But for the surface, we had good equilibration and good results, and definitely some of these schemes are candidates for operation in the future. Another aspect of Primavera was looking at the equivalence between stochastic physics and resolution, with the idea that perhaps stochastic physics, because it tries to represent the subgrid variability and the missing processes that are in this subgrid space, stochastic physics can be seen as a surrogate for resolution, despite costing a very, very small amount numerically compared to increasing the resolution. And what I did here is looking at EC Earth, I compared 5 different resolutions. These are again the tropical cyclone storm tracks globally. So these are how many storms go through a region per year. And I look at 5 resolutions with and without stochastic physics, and this is the difference. And what stochastic physics does to hurricanes is very similar to resolution. It increases the number of hurricanes, it increases the interannual variability, and it does act a little bit like an in-between resolution. We could say that this distribution might sit between one resolution and the next higher up. So in many ways, it is an interesting surrogate for resolution and an interesting way to understand what resolution does. However, the way these storms are produced is rather different if we now follow the environmental drivers. And I have a paper that is probably going to be published in Journal of Climate this spring to explain what this is. In terms of climate change, I showed you before that the climate change in the Primavera-HighResMIP models was mostly showing an increase in the Pacific, a decrease in the Pacific, and an increase in the North Atlantic. In fact, as we look through the EC Earth models where we don't use stochastic physics, we see something rather similar. But if we then add stochastic physics to that, we start to see some interesting dipoles, where we see, for instance, in the West Pacific an increase and the East Pacific a decrease. So stochastic physics tends to generate a local decrease with climate change that is not seen in the equivalent resolution simulation. So this tells us that the future might look somewhat different if we treat these subgrid phenomena in a different way than we do when we just stay with a deterministic model. So this is a very interesting technique to use alongside resolution. And I'll just skip to some of the diamond results and I close. As I said, we developed models in this sub 5 kilometer range. And we have a picture here of what one of the forecast days looks like at 5 kilometers from all the models that participated in Diamond. One of these is a satellite image. So these are render clouds. And the idea is that in a Turing test, we wouldn't be able to tell which one is a model and which one is a satellite image. The notion here is to follow for the next generation the ideas that were expressed by Matsuno, with sort of the tropical weather being the next frontier in a credible climate simulation. So we surpassed mid-latitude cyclones when we went across the sort of 200-kilometer resolution boundary. And now we are going down towards 1 kilometer with the idea we would mostly resolve clouds. This resolution has strong implications for how realistic the hurricanes are. This is an example of the wind pressure relationship in black observations. In blue, diamond simulation. These are the other models that were in Primavera, which fail very much to reproduce the strong circulation around hurricanes, and also the distribution of the categories. In diamond at 5 kilometers, we started to have a realistic number of category 4 hurricanes, and also the intensity, so how deep the low pressure is and how strong the winds are, and also the precipitation field around the hurricanes. And we have a paper that is about to be published that looks at these relationships in most of the diamond models. So again, the notion of being able to simulate intense storms in the context of the climate system with future models. And that's basically where we are going with the follow-on to Primavera. So I'll just summarize here to say that, well, looking at it in terms of HighResMIP in heterogeneous ensemble agreement, what has happened is that some of the historic biases have been finally reduced. We see them in the sea, we see them in the atmosphere, and also on land. And also we see them in the land-atmosphere coupling and the ocean-atmosphere coupling. The models agree in the response to increase the resolution over very large portions of the globe. So regionally, there are very consistent signals that all the models produce. And we can attribute the agreement to specific processes like the interactions with boundary currents or the interaction with mountains. There is evidence of stronger coupling between the climate system components over narrow regions across the globe. I showed you the land-atmosphere coupling becoming narrower and shifted spatially, particularly over Africa. These simulations are being produced in a very consistent way because the protocol was very strict. We also ran a small ensemble, so not as big as we wished we could do. Mostly we ran 3 ensemble members, and in the future we might want to run many more of those. There is now a very large global data set that can be exploited to produce event sets, for instance, catalogs of hurricanes. About 5,000 years of 20-kilometer simulations available on Jasmine and also through the CIMIP portals. For tropical cyclones, there is about 500,000 tropical cyclones available to be studied and to put into catalogs and composites and all that. We need to be very consistent when we apply these ideas, for instance, the global teleconnections, in how we go from this to impact. So for instance, from hazard to risk, that we also look at risk in a teleconnected way. And this is the idea of making these data sets available so that industry or governments can use them. All to say that resolution, no panacea. There are still very substantial errors and there are still very substantial inadequacies in these 20-kilometer models. But I think the benefits in terms of understanding, especially understanding that it's based on processes, outweighs the cost and shortcomings. We'll continue to produce analysis in the future. There are many years to go in terms of analysis of these data sets. As I said, order of 10 petabytes of data to look through, and to further understand the role of these processes in the climate system, and also how this affects climate change. And I showed you an example of ocean eddies affecting our projections of extreme precipitation over Europe or the transport by cyclones. And this requires a community approach. We were able to produce about 100 publications in Primavera But to exploit the data, we need the whole community to basically attack. So you're very welcome to sign up to Jasmine and do analysis of our data sets. And I'll stop here.